The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
Okay, so on to today's topic. Today we're going to be focusing on issues associated with oxidation and reduction half reactions. And I want you to think back to my first lecture where I really talked a lot about how unifying the concepts were that stemmed from the ideas of Gilbert Newton Lewis, because we talked about acid-base, donor-acceptor, electrophile, nucleophile, and oxidant-reductant, all as parallel concepts with the related theme there being what's going on with the electrons in the system. And it's really important to consider not simply the reactions that occur between molecules, but also the reactions that occur when electrons coming from molecules or coming from ions or coming from metals are connected up in some kind of external circuit that can be interfaced then to some real world problems through the mechanism of electrochemistry. And so we'll talk today about some of the basic concepts that you'll need. This will be the equipment that you can use to do future research to solve the world's energy problems. Okay, so this is going to be good, and it's pretty straightforward. I want to give you an example of a reaction that can be decomposed into half reactions. And that is the reaction of magnesium metal with carbon dioxide going to, and this will be 2 equivalents of magnesium, going to 2 magnesium O2 plus elemental carbon. Now, this is an important reaction in that it contains one molecule carbon dioxide that is a really critical energy and environment molecule that we worry a lot about today, because I'll emphasize this in a few points during my lecture today, but we want to be able to find ways of producing energy that don't simultaneously produce a whole lot of CO2 that goes up into the atmosphere and is a greenhouse gas. Okay, so we'll talk about that, and I'd like you to just start thinking in the background of your mind right now about the molecules, if you can list them, that are really important to energy concerns today. With this reaction, we can decompose this into the following half reactions. We can see that it can be written as carbon dioxide plus 4 electrons plus 4 protons going to carbon plus 2 H2O. And then simultaneously we can also write 2 magnesium plus 2 H2O going to magnesium 2 equivalents O plus 4 H plus 4 electrons. Okay, so although the reaction that one may actually carry out would be the one on top here, that reaction can be separated out into the parts that are associated with oxidation and the parts that are associated with reduction. And so down here in equation 1, we see that CO2 is undergoing reduction by 4 electrons. This is a 4-electron process. And down here in equation 2, what we're seeing is that this magnesium metal is ultimately serving as a source of 4 electrons in that process. Each magnesium going to magnesium 2+. So there's implied here that we're going to be able to know something also about oxidation states. And so as we talk about oxidation reduction processes, I want you to also, if necessary, review what you know about the assignment of oxidation states in systems. But by writing this out, you can see that on the left side of equation 1, electrons are going in, and on the right side of equation 2, electrons are coming out. And really, if you can keep track of what are the supply of the electrons and where's the demand for the electrons in the overall system, you'll really have a good feeling for how these processes physically may be taking place. And then up here on top, this is the sum of those two equations, 1 plus 2. Okay. And that's typical of how we write oxidation reduction half reactions. And when we consider a pair of half reactions, one of the things that we're really interested in is the potential difference. And that is to say, if we have some way physically of sequestering the two individual half reactions into different containers, and if we allow them to communicate, but we don't allow the reaction to proceed to any significant extent, we can measure this. So we can measure it when the reaction is not allowed to proceed to a significant extent. And the reason for that latter caveat is that when you put into communication two sequestered cells that are each poised, one to undergo a reduction and one to undergo an oxidation, then if you put them into contact and let that reaction start to proceed, you can see that that reaction would proceed until such time as equilibrium is reached. And so all throughout that process, the potential difference between the two would be changing until it stops changing. And when it stops changing, we would have reached equilibrium. So the two independent half reactions at the beginning have their own potential, the degree to which they're poised to undergo oxidation or reduction. And then how do we do this? Well, you're going to see that we can use a thing called a salt bridge. And with a salt bridge, we can allow for not only communication of the electrons from one of the half reaction cells to the other, but we're also going to need to allow for the movement of ions. Okay? This permits ion movement. And this requirement for ion movement, stems from the necessity to maintain electroneutrality, charge neutrality in each of the two cells that we have, each of the two compartments of the electrochemical cell that we're going to create. And in reference to electrochemical cells, there are lots of different types of electrochemical cells. And today we're going to be discussing two of these in particular. I'm going to start out by talking about what's called a galvanic cell. And then I'm going to talk about how you can use galvanic cells to measure standard properties of oxidation reduction half reactions. And then after we do that, we're going to talk about the properties of certain redox active systems. And then finally, I'll finish up by talking about another type of electrochemical cell, and this will be an electrolytic cell. So let's look at a galvanic cell. Let me just use this slightly different color here. Last week I left my blue chalk in here. Gone. Oh well. Down one color. If anyone can find that blue chalk for me, I'll be very appreciative. Okay. As I've been alluding to, we can set up an electrochemical cell, in this case called a galvanic cell, in which we sequester two different half reactions to the different compartments. And then we're going to need for control of the communication between the two compartments. And we'll do that in the following way. What I'm representing here is a piece of metallic zinc. And the way I've drawn it, it's supposed to be like a simple strip of zinc metal, to which we could attach some alligator clips, and we can run an external piece of wire over to the other side, and we can interpose here some kind of a meter. So this round unit here could be either a voltmeter or an ammeter to measure respectively voltage or current in a system like this. And then over on the other side, we'll have a different electrode. And this electrode will be made of copper, metallic copper. And then I've got to have my salt bridge so that we can maintain electroneutrality in these solutions that we're going to have on both sides in the two separate compartments. So there's my salt bridge, and this might contain an electrolyte such as potassium nitrate, and that electrolyte would be suspended in a gelatinous medium like agar, for example. And what we're going to be interested in we're going to be interested in the directionality of the electron flow in a system like this. We're going to be interested in the potential that gets set up when the electrons flow in a system like this. And we're going to want to know which side's the anode and which side is the cathode, and what are the equations for the reactions that are taking place at the side that's the anode and at the side that's the cathode. So let's look at that. Let me just point out that if I had blue, I would be indicating the aqueous solution here in blue. So you'll just have to, well, maybe those of you who are colorblind will think that's blue. But anyway, this is, the idea is that we've got an aqueous solution here on both sides. And this one over on the right is going to start off with some concentration of copper 2 ions. In solution. So some molarity of copper 2 will be present in the solution over here on the right-hand side where we have the copper electrode. Inside the salt bridge, we have potassium ions and potassium cations and nitrate anions that can go into solution on either side to balance the charge changes that are taking place as oxidation reduction reactions happen on the left-hand side and on the right-hand side of this electrochemical cell, which is a galvanic cell. And so what we find is that you turn this, you let this go into contact briefly, and you would measure for this cell 1.1 volts. Okay? And so that's the magnitude of the potential difference between the two half reactions that are present on both sides of the cell. And furthermore, we would see that the electrons are starting out over here, and they're going this way around the circuit. And that tells us that what we have on the left electrode at zinc is going to be called our anode. And that's because at the anode, oxidation is taking place because metallic zinc is undergoing oxidation, becoming zinc 2+, and providing, in so doing, the two electrons for every zinc that it gets oxidized. So what you can think of as happening over here on the side that we call the anode is that you've got this piece of zinc metal, right? And in order for electrons to start coming out to the external circuit, for every 2 electrons that comes around to the outside of the circuit, you have a single zinc 2+ ion that jumps into solution. Okay? So a piece of zinc jumps off of the surface of the electrode. That zinc atom leaves as the zinc 2+ ion. That supplies 2 electrons to the external circuit. And at the same time, to balance charge, we would have to have from the salt bridge entering solution 2 NO3-, 2 nitrate anions have to come, because they're singly charged, 2 of them, have to come out of the salt bridge and into solution every time a zinc 2+ drops away from the electrode and starts flowing into the external circuit. Okay? And electrons go around. The initial voltage, when the reaction hasn't proceeded to any significant extent, is this 1.1 volts. So we've measured the potential difference between the two half reactions. Here's one of these half reactions. At the other side, if on the left side we have an electrode that is the anode, then on the right-hand side we must have an electrode that is the cathode. And we must have reduction occurring there. And what is getting reduced? Well, as electrons appear down here at this electrode, they can encounter a copper 2+ ion in solution that can then become part of the surface of the electrode as a copper metal atom. So in other words, we're depleting the surface of this piece of metallic zinc over here, and zinc ions are going into solution. And on the right-hand side, copper ions are coming from solution and becoming incorporated into the electrode itself. And so if you ran this reaction for a while, and then you took the 2 pieces of metal, zinc and copper, that you had used to set up the galvanic cell, you could weigh them, and you could see that the zinc electrode would have gotten lighter, and the copper electrode would have gotten heavier. And so that's also the basis for the technique of electroplating, where you can take one metal and cover over the surface of it with a thin layer of another metal. So here we're just putting a new layer of copper on the surface of this copper electrode, and we're depleting what we would call over on the left the sacrificial zinc anode. And this reaction then over on the right-hand side is copper 2 plus 2 electrons going to copper metal. Okay, so that's a prototypical example of a galvanic cell. And in setting that up and thinking about what's happening there in terms of depletion of one electrode so that the other one can be increased in mass, you may be aware that you know of places where this principle is actually used in construction, for example. You know, there are large steel bridges that are constructed, and one doesn't want those to oxidize away and to become fragile in their structure so that the bridges break down and the bridges are not safe anymore, shall we say. And so what's often done there is large pieces of zinc actually are put into electrical contact with the metal of the bridge so that it's the zinc that actually gets oxidized away as a sacrificial anode instead of the bridge itself. The same for any of you who are sailors or boaters in general. You probably know that zinc anodes are present usually in several places on boats so that electrolysis doesn't occur and corrode away the metal parts of your boat. And instead, the zinc sacrificial anode is oxidized away and is a source of electrons. So that's an important principle. Once you've started looking at some different kinds of oxidation reduction half reactions, you're gonna want to know, well, just how oxidizing is something, or just how reducing is something. And in order to do this, we need to pick one particular half reaction that will serve as our universal standard. And to that half reaction, we will compare everything else. And so that brings us to a discussion of standard reduction potentials, or standard potentials. For this, I'm going to make another galvanic cell. Got purple for this. And concerning this galvanic cell, we will have a number of the same questions that we've had before. But the one that we're going to be using on the right-hand side is going to be very special. Let me indicate our water line again in green. And I'm going to put in a salt bridge into the system. And I'll have an electrode here on the left, and another electrode over here on the right. We'll connect up these electrodes using alligator clips. We will need an external circuit with a meter, so we'll be able to compare the potential of the two half reactions of interest. But then over here on the right, this electrode is going to be a little different because this one is going to have something like a test tube inverted over it, because the reaction that we'll talk about here, in fact, does involve a gas. And that gas is hydrogen. Another one of our important energy molecules to be talking about in the context of today's lecture. So, as at the end, I'd like to see if you've got a list of energy molecules collected from today's lecture. But also, we're going to choose as the electrode material here, this metal piece of material, this is going to be platinum. And the reason we're going to choose platinum, a very common electrode material, is that platinum's a noble metal, so-called noble metal. And that means that it's quite impervious to most chemical reactions. So over there, we were talking about zinc and copper electrodes that themselves do change during the reaction. And over here, we want to have a piece of metal that can provide the valuable function of giving us electrical contact of the chemical reactions on the two sides, but an electrode which will remain clean and unchanged at its surface throughout the course of the reaction. So we use a platinum electrode over here, and you can see that with this inverted test tube through which the wire passes, and with some kind of a provision for a sidearm attachment here, we can hook up a cylinder of H2 gas, and we can start bubbling H2 over this electrode like this, so that actually we'll have bubbles of H2 coming out like that. So in fact, this solution over here will be saturated with H2, and a further consideration for our reference electrode, which is going to be known as the standard hydrogen electrode, or SHE. That's the electrode against which everything else is going to be compared. And it also has in the solution here 1.0 molar H3O plus. So indeed, it is a very strongly acidic medium. And what we're measuring over on the right-hand side is a half reaction that may correspond either to 2H plus 2 electrons going to H2, and that will be the case if this side is the cathode. But if this side turns out to be the anode, then we would be measuring the opposite reaction, and I'll talk more about that in a second. But let's say, for example, that our electrode over here is in fact made of zinc. If our electrode over here is made of zinc, and we may have zinc 2 plus in solution here, and we may again have something like potassium nitrate or some other electrolyte present in our salt bridge, then what we can do is put these things briefly into contact, and we want to know two things. We want to know what's the magnitude of the potential difference, and what's the direction in which the electrons are flowing, so that we know which one is the cathode and which one is the anode. And in this particular case, the direction of electron flow is, as before, away from the zinc. Okay, so once again, zinc atoms are jumping off the surface of the electrode as zinc 2 plus ions, and every time that happens, 2 electrons go into the external circuit, and they come around here, and the chemical reaction that occurs here in this case is that those 2 electrons that came from one of the zinc atoms react, as shown here, with 2 H plus ions to make H2. And so we know the direction of electron flow. We know the exact reactions that are taking place on the left and on the right. And we know that for this particular choice of substances, our anode is on the left and our cathode is on the right. And let me come over here. There's another way that I can write this cell. And so I'd like to introduce cell notation to you. And that will be like this. We will have zinc, and then a solid line, and then zinc 2 plus, and then a solid double vertical line, and then H plus, another solid vertical line, H2, and then another solid line, and then platinum. Okay, so that's the way I set that up. We could actually add another solid line here and put platinum over here. The thing that I want you to recognize about this notation for galvanic cells is that the solid single lines represent interfaces, direct contacts between things. Here it would be a platinum solid electrode connected with solid zinc, possibly. And then with the way I drew it over there, it would just be solid zinc, no platinum on the left. And then this solid line represents a solid liquid interface because the electrode is dipped into a solution that contains zinc 2 ions. And that is in communication with the other half of this electrochemical cell by a salt bridge, and the salt bridge is represented by the double vertical line. And then we have in solution protons, and then a solid liquid, well actually in this case a solid, a liquid gas interface to the gaseous H2, and H2 is also dissolved. In order for this to be used as a reference electrode, we have to pick standard conditions, and so we're usually talking about 1 atmosphere of hydrogen for the standard hydrogen electrode. And we're talking about a concentration of 1.0 molar of our strong acid. And so those are our standard conditions along with 25 degrees C. And then this solution that contains the protons and the hydrogen gas is in a solution solid interface with the solid platinum electrode that isn't going to be undergoing any change. So these are the types of cell notations that you will encounter when looking into electrochemistry. And we've found out that zinc, the left side where the zinc metal is going to zinc 2 plus is our anode, and also the potential difference when we measure it using our voltmeter right here by turning on the contact very briefly is around 0.763 volts. Okay, so that's the magnitude of our potential difference, and this is equal to delta E0 cell. Okay, when I write E0, that means standard potential. And this is written as a delta here because that's the difference between the potentials for the two half reactions that we've got written up there. But it's a very simple difference precisely because the standard hydrogen electrode is our reference electrode. So over here, we want to write the definition of standard cell potential. and that is delta E0 for your cell is equal to delta E0 for your cathode minus, sorry, this is not delta here, just E0 for your cathode minus E0 for your anode. But E0 for the standard hydrogen electrode, because this is our reference electrode, is equal to 0 at all temperatures. And that is by definition. So the standard potential for that set of conditions that constitutes our standard hydrogen electrode is taken as the 0 of potential for comparison with any other type of half cell that you might be able to consider. And so we can see further that in this particular case, where we have our cathode as the standard hydrogen electrode, we have 0 and minus E0 for the anode, which we measured as 0.763 volts. And that means that for the reaction zinc going to zinc 2 plus 2 electrons, which is our anodic reaction, we have a standard potential of minus 0.763 volts. Okay, and generally what you're going to be interested in as you consider different kinds of substances from throughout the periodic table with reference to their ability to take place in oxidation reduction reactions is you're going to want to know what's their standard potential. You're not going to always have a system that you want to consider that's under standard conditions. So these standard potentials always are referenced to some standard conditions, as I mentioned specifically for the standard hydrogen electrode. And so part of next lecture on Monday is going to be, we're going to show you how to handle systems that aren't under standard conditions, okay? Because then you can handle some real practical problems. But let's look at a different type of cell. Let's write down the following cell. Okay, this new cell that I've written the cell notation for, instead of drawing up the whole diagram of this galvanic cell, happens to be one in which we've got platinum electrodes on both sides. Here we have the silver plus redox couple on the left-hand side, and we have the redox couple of H plus with H2 on the right-hand side. So the right-hand side corresponds to the standard hydrogen electrode. And the left-hand side is a new redox couple, or a new half reaction that we want to compare to the standard hydrogen electrode, so that we'll know on an absolute scale where it falls relative to all the other half reactions we might want to measure. So we want to know which way did the electrons flow. And in this case, it turns out that the direction of electron flow is this way. Okay, so this is the opposite of what we talked about in the case of comparing zinc to the standard hydrogen electrode. Electron flow has been reversed, and what that means is that this over here, the SHE, is now our anode, right? And now the silver plus electrode is our cathode. And we want to know not only the direction of electron flow. The direction of electron flow tells us what's doing the reduction and what's doing the oxidation. But we also want to know the magnitude. And this one turns out to be this delta E cell is equal to 0.8 volts. Okay? And by the definition of standard cell potentials that I gave you over there, you can see that what we're getting now, because the electron flow is reversed, our sign is reversed, and so our E0 for the reaction silver plus an electron going to silver is equal to 0.8 volts, positive. Notice that the zinc 2 plus couple was negative with respect to the standard hydrogen electrode, but because the electron flow is reversed for silver plus silver redox couple, we now have a positive potential relative to the standard hydrogen electrode. Okay. So what we would like to arrive at is a nice big table where we look at standard potential with reference to this standard hydrogen electrode, which is our zero of potential. Okay, and you'll be able to find a table like this in your book. What we found is that zinc is down here at minus 0.763. So that was zinc 2 plus at a negative potential relative to hydrogen plus electrons. We found that up here at plus 0.8, we have the silver plus redox couple. These are thermodynamic quantities, so you can look on a table of standard reduction potentials and you can tell which direction electrons will flow if you set up cells that involve those redox half reactions. Another electrode that we used today was copper 2 plus, combining with 2 electrons to give copper metal. Turns out that one's positive also by about positive 0.3 volts. So you see hydrogen is here, and it reduces silver plus. Hydrogen reduces silver plus to silver because it's up there. Zinc is down here. Zinc also serves as an anode with respect to any one of those three, because all of those three are at a potential positive relative to zinc on this scale of standard reduction potentials. You can also have some other potentials, like way down here at about minus 2.7 volts is the sodium plus redox couple. Way down there at minus 2.7. That's why sodium is so much fun to heave into a body of water. Because then, it's fantastic. You get reduction of the protons to make hydrogen, which then explodes. So it's just fantastic. And some of you may know that there is an annual. I'm not recommending that you do this, by the way. But you can see how negative the potential is down here. Metallic sodium is a very strong reducing agent indeed. A very important reaction is up here at about plus 1.23 volts relative to the standard hydrogen electrode. And this important reaction is oxygen plus 4H plus 4 electrons going to 2H2O. Okay. So this plus 1.23 volts is very important because in the time remaining, I'm not going to be able to tell you about electrolysis. So I believe next hour I will start off by talking about electrolysis. And if you can do electrolysis using oxidizing and reducing equivalents that derive from photovoltaic cells, so you're converting sunlight into separated electron-hole pairs, you can drive a reaction like this the other way and learn how to make oxygen from water and ultimately also hydrogen from water. So we'll talk about that a little bit next time. Have a nice weekend.